Start the recording. Okay. Last time, of course, we finished up looking at the intro to computational complexity. And although at the beginning it looks a little bit like, math and functions, and although that's true, the level that we're going to care about in this course is very, very, like, we simplified it quite a bit. We saw how we can look at functions and code to kind of get a sense of what the T of n was, but then we would often go from that or just straight to like the big O. Like if we saw nested for loops, sometimes we think like, okay, is that like n squared? But of course we saw something that was like n log n, which was interesting. And we'll see other algorithms that are like that going forward in the class. And a big message here is we want our algorithms to grow as slowly as possible in relation to n. That's good. That's a good thing. We like that. In terms of time, like computational complexity. Anyways, now we're going to move on to talking about queues. The queues, now we're back to like a data structure. We saw stacks, and we built an array stack, and we built a linked stack, right? They are both stacks. It's just one was built where the backend used an array to hold on to the information, and the other one was built such that the backend used a series of connected nodes, a series of linked nodes that held on to the information for us. Well, now we're going to build a queue, which is a different data structure. It's a simple one. It's linear. It's perhaps a little bit more complex than a stack, but not overly so. And the good news is, chances are everyone in here is familiar with the idea of a queue. I mean, how many times have you ever stand in line for anything ever? Maybe you went to Starbucks this morning, or you hit Tim Hortons or McDonald's, I don't know. And you stand in line, and like it's a first come first serve basis, right? If you're the first one there, you're the first one that gets served. And if someone shows up behind you, they stand up behind you. You're going to go before them, but they go after you, and anyone who's behind them goes after them. As people show up, they enter the back of the line, and then they wait until it's their turn. When people are getting served next, they leave from the front of the line, assuming we're following the rules of the line. We've all been in lines where people are trying to break the rules, and of course that is a wildly socially unacceptable thing to do. Anyways, let's have a look at some slides. All right, linked. First, we're going to talk about queues as an idea, and then we'll look at one implementation of a queue, a linked implementation. Take a wild guess if we're going to look at another implementation using some other container and what that container might be. So a queue, the point is, well, what are queues? Let's define a queue and its operations, and we'll use a queue to solve some problems. I'll warn you, the problems that we're going to look at are, similarly with the stack, are kind of contrived, especially because, we're already familiar with queues, but we'll do it anyways. And we'll examine the linked queue implementation, and my mouse is stuck under my other keyboard, and talk a little bit about the operations complexity, because now we know all about computational complexity, so let's talk about the computational complexity as we're going. All right, so a queue. It's a collection of elements where things that are added go to the end, the rear, the tail, whatever we want to call it. And things that are removed come out of the front, or the head of the queue. This is called a first in, first out data structure. First come, first serve. The first one there is the first one that's going to come out, and so on and so on and so on. So unlike the stack, where, like, if we have the stack here, it grew, like, if you entered the stack, you'd go to the top, and then maybe, you leave. Like, all the action happens from one side, where a queue, it's kind of like this, right? As things show up, they enter, and then they'll leave the front. So now this is the new front, and then this would be the new front, and this would be, oh, now it's empty, Okay, queue operations. Enqueue. This is how we add something. Usually with all these data structures, we're going to have a way to add something, have a way to remove something, have a way to, like, look at something but leave it there, get its size, ask if it's empty. These are things we're going to typically have for all these data structures we're building. So in queue, this is how we add something. It goes to the end. This is kind of like the idea of push for a stack, except of course, the stack, everything happens from one end, where the queue, it happens at both ends. And then dequeue, remove something. Something's leaving the stack. It comes from the front of the queue, and it's kind of like pop from the stack, but of course, it happens at the opposite end of where the Inqueue happened. We'll have like a first operation, examine the next element. This is like peek, you know. It looks at the front or head of the queue, but it leaves it there. Size, how many things are there, and is empty. Remember, we are not allowed, like you might say, well, but I could implement it where I can access the second thing in the queue. Yeah, you could, but then you're breaking the rules of what a queue is. You could do that, but then it's not a queue as we're defining it here. It's, if you want to do that, if you want to make your super fancy queue where you can do that, go ahead. Just don't call it a queue, because this is the defined queue. Simple like this. So here's an example, in case you weren't painfully aware. Here's some people in line. I don't know, maybe this is McDonald's or something. Woo. And then someone shows up. Oh, I lost my McDonald's sign. Well, that's okay. Someone shows up, they enter at the end because they're a good, upstanding citizen who knows how to line up for things. Now, this guy looks like they're getting served next at McDonald's. Okay, perfect. So they leave. So you'll see, like, well, now we've got two of these guys that are two black stick people, and then the cyan or turquoise, whatever color that is, stick person leaves because that's, you know, they left. So real life examples of queues: waiting in line at checkout, cars at a stoplight, keyboard input buffers. You know, like when I start typing, we got to keep track of the order in which the keys came in. Printer queues. I mean, I'm getting overly technical now. GUI events. Ooh. Basically, anywhere where there's a first come, first serve rule. I mean, like, look, I listed here 1, 2, 3, 4, 5, 6, actually not even 5 things. We could play this game forever. We could keep adding more and more and more things to this list, but because of course there are so many examples of this. Simple uses in computing, maybe we're doing like a little simulation study, right? I want to optimize the flow of traffic through a city by simulating the system. Or how many checkout lanes do we have to have open to optimize throughput for a given scenario? So imagine you're at the Science Atlantic, right? And you're in you know, they want to maximize the throughput of customers through the cashier lines. So let's assume a couple things. Every customer arrives every 15 seconds, and processing takes 2 minutes. Obviously, this is a very simple model. Somebody might take 1 minute, somebody might take 3 minutes. And if you're at this Atlantic Superstore that I know, maybe they know each other and they talk for 5 minutes before you get served. I don't know. But we'll just say on average 2 minutes. Why? Because sure, it's a simple model. So what are we gonna do? Well, if we have one cashier open and we run the simulation such that a new one shows up every 15 seconds and we have 2 minute processing time, one cashier, this is the average time a person's gonna take in seconds for the duration of our simulation. But if we have 2 cashiers, it looks like we have this number, 3, this number, and so on and so on and so on, until it looks like we kind of converge here on the number 120. If we had 11, I'm going to bet that this says 120. In fact, I don't even need to bet. I know that this is going to be the case. Anyone have any idea why that 120 popped up? Type it in the chat if you know. Yes, there you go. Congratulations, one of us can do basic arithmetic. You're right. There is 120 seconds and 2 minutes. Each person takes 2 minutes, so the best we can do is a 120 second processing time. We can't do better than this. So if I truly want to maximize inputs here, or pardon me, throughput here, and I'm in charge of how many cashiers are going to be working right now, how many cashiers would I conclude is the right number to have? 8. If I'm maximizing throughput. Because if I add 9, I'm not getting any faster speeds, but I'm paying another person to work. So I'm going to want 8. This is the one, not this one. This one, this one, this one. This makes the manager happy. And here, a Cypher. You're probably familiar with these. You know, you probably played with them when you were little or something. A Caesar Cypher is a very simple, easy way to encode a message. All you got to do is shift each letter in the message by some constant amount k. I think the typical one is 3, but if k is 5, if k is 5, A's will become F's, B's will become G's, C's will become H's, and so on. Why? Well, because if we have like A, B, C, D, E, F, G, H, dot, 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 well, I want to shift this down 5. So A's 1, 2, 3, 4, 5, right? So is 5, B's become G's, C's become H's. So we can encode our messages by shifting 5. And then I could easily decode this message by shifting 5 the other way. Anyways, and it loops. This is an important feature too. It loops. So if we're at like Z, it would go Z, okay, 1, 2, 3, 4, 5. So it would go dot, 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 to the E. It loops. So if this is a message, what does this say? Okay, well, let's, oh my goodness. Well, A, B, C, D, E, F, G, H, I, J, K. You know what? Forget it. I'm too lazy. If you want, honestly, I don't even remember what this is. Maybe I have it down here. All right. I honestly don't. I bet this says like, I love CS or something. I bet. And the only reason I'm guessing that is because it seems like something I would put in here. So what's 5 before N? I, J, K, L, M, N. Okay, L, M, N, O, P, Q. Yeah. And then C, D. Well, we know C goes to H. Yeah, it's definitely I love CS. Don't you? Look at that. I encoded that message. So we can make a much better cipher by changing K, but like having it repeat. So we can have this as the key. Shift the first letter by 3, then the next one by 1, then the next one by 7, then by 4, then by 2, then by 5, then by 3, then by 1, then by 7, 4, 2, 5, 3, 1, 7, 4, 2, 5, 3, and so on and so on and so on and so on and so on. So now it becomes harder to decode because if we go back here, I mean, this is, if you know this is a Caesar cipher, it's easy to decode. In fact, how long would it take you? In fact, let's have some fun here. Okay, I'm gonna make this a complicated question with a very simple answer. What is the computational complexity? You see a message like this, okay? And you know it's a Caesar cipher with K equal to X, but we don't know what X is. What is X? We know it is some number that tells us to shift, and we'll assume K is consistent. It's not the case where we have a rotating K. It's some value. What is the computational complexity of decoding your message of length? Let's say this message has length M. So we got 3 different answers. And so Cole, when you said N, what do you mean? What is N in this case? Or did you just throw linear out because why not? Length of the code. Okay, yes. So I called it M. So let's say Cole and so we have 2 M's. Okay, the length of the message. So why? Well, here's the thing. Felix is right in that, like, well, at worst we have to check 23 things, right? We try K equals 0, and then try K equals 1, then try K equals 2. But this is a constant number. The number of letters we have in the English alphabet hasn't changed in a while, and they're probably not going to change for quite a long time. So this value right here isn't going to change. It's 23. And what do we know about anything that has a constant value? Well, that right there is like, that's like order 1. That's 1. But we have to also read the whole string to know if it has been decoded properly. And the time it would take to read the string is going to be on the order of the length of the string. And if I said the length of the string is M, well then it would be just order M. We have to read the whole string. Now you might say, you know, technically you don't need to know how long that string, like you don't need to read the whole string to know that you've got it decoded. You know, you don't need to know, you don't need to read the whole thing. If this string is like 1,000,000,000 letters long, you could probably get away with reading much fewer than that to know if you picked the right K. But I don't know, maybe computationally this is the simplest way to implement it. Or at the same time, you know, like if n is relatively small, which is usually not the cases that we care about, if n is relatively small, it's still going to grow with n. But I suppose as n gets hilariously large, we could probably get away with reading much fewer and fewer and fewer proportion of the whole string. Long story short, to keep it simple, this would be like order m, where m is the length of that string. Because we need to check 23 things. So really, we need to check m 23 times. Well, what do we care about this? We don't. I heard a boop. 26 letters in the alphabet. All right, well, what did I say, 24? Yikes. Well, you said 21. Whatever. Let's pretend we're using the simplified English, where we actually only have 21 characters. Oh my goodness, how embarrassing. You know what's even worse? Is it took how long for someone to be like, oh, wait a minute, no, there's 26 letters. Gee, that'll teach me from trusting you, Felix. Come on. Whatever, at least we figured it out. Point is, but here's the thing, right? If this is m times k, or no, we shouldn't put k, m times j, but if we know j is some constant, you know, heck, maybe I should say like mc, but c is some constant value, I don't care how many letters there are. As long as the number of letters is like fixed and it's not changing, it's just m. There we go. So you know what? It didn't matter in the end for how long it'll take to decode. So it doesn't even matter. Okay. So yeah, we can have this rotating. So we shift the first letter by 3, then by 1, then by 7, then 4, 2, 5, then start over, 3, 1, 7, dot, 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 dot. So let's say we have this encoded message. Novangajal mu live, whatever that means, right? Well, I would know that I decode the n by shifting 3, then that by 1, then that by 7, then that by 4, then that by 2, then that by 5, then that by 3, dot, 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 dot. So where do you think the queue is going to be used? I mean, if it's not obvious, it's fine, because this is, again, kind of a contrived example, but where can you envision a queue? The idea of the first in, first out data structure, where can you envision that queue being used here? Throw a couple things in the chat. We'll see if we get any good answers. Okay, yes, absolutely. Building the words one by one. You might be right depending on what you mean by that, but yeah, Alex is right. Well, here's what we'll do. I have some arbitrary string of length m, let's say. I have my key, my rotating key of how many things? 1, 2, 3, 4, 5, 6. I have a 6 length rotating key. So what I'll do is if I have like my queue like this, I will start with 3, 1, 7, 4, 2, 5. Jeez, I don't know what's up with my computer. It tends to like to read in these random left movements, whether I'm using this fancy pen or my mouse. But what I'll do is I will dequeue the 3, so this comes out. I will shift the first letter by 3, and then I'll put the 3 back in here. Then the next time I take out the 1, shift by 1, and then add the 1. Take out the 7, shift by 7, add the 7. And you'll see that like once we finish, we'll still have the 3, 1, 7, and so on and so on and so on and so on and so on. So we're in great shape. So we have the idea down fantastically. I mean, chances are you had the idea of how a queue works well before I gave you this lecture. I'm willing to also bet that at no point in your life have you thought more about a queue than you have right now. In fact, you probably haven't been thinking about it too much because you haven't had to. But this is probably the most you've ever had someone talk to you about a queue for an extended period of time. Because you know how they work. So now we need to actually start thinking about how we implement these things inside our computers with some code. I mean, we know how to implement them in real life. All right, start lining up there, everybody. There, done. People will figure it out. Their brains are capable of computing how to do that. But we need to actually write the code because the computers are too stupid. I can't tell the computer make a queue because, well, it doesn't know. I need to tell it how. Remember, though, we talked about Inqueue, Dequeue, first, size is empty. That is what it can do. We have no idea, though, at this stage, how it does what it does inside the computer. We got to keep an eye on the time here. I tend to... Oh, no, we're in great shape. We need a container. Well, let's start with a linked structure. You know, I know last time when the stacks, we started with the array, and then we did the linked structure. Well, here, let's start with the linked structure, and then maybe we'll look at arrays later. We will. So we need something to keep track of the front. All right, just have a pointer, keeping track of the front of the queue. And the rear, we need something to keep track of the rear because we need to know where we add things after. So I'll just have a pointer to the end. Easy. We need to keep track of the size. All right, just an integer. So here's the idea. We'll have some queue object or a pointer to some queue object. So this right here would be an instance of the queue. Its count is 4. Why? Well, there's 1, 2, 3, 4 things in it. Actually, I should be counting. I should be doing this. 1, 2, 3, 4. The front, well, it's a pointer to the beginning, and this is where things are going to leave. And then we have rear, which is a pointer to the end, and that's where we're going to add things. New elements come. Well, we just update. We add the new thing to the end and update the rear. And update the count. We dequeue, well, remove from the front, and then we update the count. That's it. Now, there is a funny edge case here. What happens if the queue is empty? You know, I know how to insert at the front of a linked structure, right? That's easy. That's push in the stack, in the linked stack. We've done that. We know how to add something to the end because that's easy. You just go, okay, rear set next to the new node, rear equals new node, done. But what happens if we have a case where like let's say we have an object over here where front, rear, and count is 0, front is pointing to null, and rear is pointing to null. This is a funny edge case. And what happens if we only have one thing in the queue? What if this is just like one node? You know, I mean, front and rear are pointing at the exact same thing. That's a funny situation. So maybe this is something we need to be aware about when we're working here. So let me ask you something too. Here's another quiz. Because we know about computational complexity now. We loved computational complexity analysis because we're computer scientists and we're nerds and we like this stuff. For those of you that are actually from the engineering side, I'm sorry, you have to pretend to be a computer scientist right now. Obviously, the engineers care about this, but traditionally, this is more of a computer science-y type thing, even though it absolutely is completely and 110% very relevant to engineering as well. In this case, what is the computational complexity of dequeuing? Is big O what? When I remove something, what is the computational complexity? What do we think? Someone's got to have an idea. 1. Absolutely it's 1. Why? Well, because it's just, okay, remove this thing and update the front to decrease count. Like, the Enqueue, or pardon me, the Dequeue does not depend in any way, shape, or form on the size of the queue. I could have the number of steps it takes to dequeue, let's say that's X steps, whatever that is. If the queue has 10 things in it and I'm dequeuing, or 1,057,000 things in it, it's still going to only take X steps. The amount of work being done does not depend on the length of the queue. So it's order 1. Now how about Enqueue? That has a complexity of what? 1. Exactly. Same idea. if it has Y steps to Enqueue, well, whether there's 10 or a bajillion, quadrillion, pazillion things in the queue, it doesn't matter. It still takes Y steps. It in no way depends on the length of the queue. Now, I'm going to add another thing. Imagine that I decided to implement my queue object without a rear pointer. Pretend this doesn't exist. I could do this. There's nothing telling me I can't do this. I could implement this. I can implement a queue that works completely. It works completely fine without this rear pointer. Oh, and I guess I should do this too. But Enqueue, like what's the computational complexity of Enqueue now? Dequeue is still going to be 1, but what is it? Yes, I heard 2 boops. So, but it's n. Why? Well, because I need to start here and then iterate all the way to the end, wherever that is, and then I can enqueue. We can implement a queue this way. There's no rule that says there must be a pointer to the end. But I'll tell you, this would be a particularly bad implementation in terms of computational complexity, because if we have an option to implement something that's order 1, constant time, or linear time, order n, you always take the order 1 time, the constant time one, if it doesn't create massive amounts of overhead in terms of like space complexity. And with this, we just create a simple pointer. That's nothing. That is nothing. So by having this extra rear pointer, I guess I can just undo everything. We have a way to jump right to the end. Where without the rear pointer, we'd have to iterate through the whole thing to get to the end, which would be very, very slow. Yes. So let's start implementing it. Let's talk about the header. Well, we're going to want our node. Yeah, we need our node class, I suppose, because it's a linked structure, and that's going to make use of the nodes. And we're going to make it generic. So we add the template class. We'll have an integer count, and then we'll have a node of type t, front, and a node pointer of type t, rear. We're going to want our constructors, and we're going to want Dequeue, Enqueue, first, size, and is empty. This is going to seem similar in spirit to the stack, because the link stack, we had I guess we didn't have 2 pointers. We only had 1 pointer because we needed to keep track of the top. But other than that, this would be like our push, pop, peak, size, and is empty. So it's very similar. So I'm actually, let's go. Let's open up Visual Studio. And I know I'm doing this all in the same project, but that's because I'm lazy. Add a new class. And we'll call it linked queue. Give it a second. Perfect. So we've got our CPP file. This is going to be left alone, remember, because we're making it generic. So we'll say template. You know what? It's going to be easier if I just do this. Just copy everything. Great. So template class T. We definitely need the nodes. The 3 attributes and our constructors. Dequeue, Enqueue, first, size is empty. Looks good. So now we need to just start implementing things. So what do we got? Well, let's create our constructor. We'll only have our default constructor. I don't really think it makes a lot of sense to have a constructor that takes any parameters. I could, but I don't think it makes sense in this scenario. So when I first create a queue, it's going to be empty. The count's going to be 0, and front and rear are both going to be pointing to nothing because there's nothing in the queue. You might find some implementations out there where an empty queue has, instead of like a null pointer, an empty queue will have a node in it, but it's a node that represents nothing. So it's not pointing to nothing, it's pointing to another thing that represents nothing, even though null already kind of represents nothing. Those implementations are fine too, but this often is a little simpler and I just like it better. And I think this is a much more common implementation as well. So there's our constructor. We're going to skip the copy constructor for now because, you know, link structure's copying, blah. We'll get there. And now we need an Enqueue. Now, there's a little bit of fancy stuff going on here, but we'll talk about it. So first things first, right here, create a new node containing the element that we're enqueuing of type T, whatever. I don't care what T is. T might be an integer or a pointer to a character. I don't care. But I'm creating this node. And if the node is empty, or pardon me, if the queue is empty, remember front and rear are pointing to nothing. So if it's empty, I'm going to say front, you're now pointing to node. You're now pointing to that new node. Otherwise, rear, set your next to node, and then rear equals node count plus plus. Now you might be thinking, hold on, I feel like you're skipping some steps there. And I will admit that this is a particularly fancy implementation that kind of lets us skip some steps, but let's draw it out. And we're going to do it line by line. First, let's do the general case, not the edge case, not the case where the queue is empty. Let me resize this window. Okay, I have a queue where we have like front, and then rear. Okay, so here's what I'm going to do. I want to add something. Okay, so I'm going to create a new thing called node that points to this new guy with whatever we have in there, E for the element. So that's line 36 here. Create the new node with thing of type E. It's not empty, right? So what are we going to do? We're going to say rear, your next is node. Okay, perfect. So rear, your next now is node. Great. Now rear, you equal node. Okay, so you don't point there anymore. You point there, and then we increase count. Perfect. Perfect. This looks like it checks out so far for me in general because the front didn't change. All we did was add something to the end and then update the pointer to what's the new end. So far, so good. So now, though, I got to be careful of undoing things because apparently that crashes my computer. If I have front and rear that point to, I'll just draw a dot to represent null. So they're both pointing to null. There's nothing in this queue. So what do we do? Well, okay, line 36 again. We create a pointer node that points to the new node of E. Great. And I guess its next points to null, but I won't draw that. So it's empty. So what do I say? Okay, I say front, you are now pointing to node. Cool. So you don't point there anymore. You point to the new node. We now skip the else, right? We don't compute the else because this condition was true, so we skip this. So now we just say, okay, rear, you're now equal to node. Okay, perfect. And increase count. Look at that. It checks out. Isn't that beautiful? That is magically beautiful if you ask me. So there we go. This all checks out. I will admit that this code here is written in a way that, well, let me put it this way. I could have written this function, this method, perhaps in a little more self-explanatory way, but I like this code right here. I think it's quite elegant and pretty. Why does isEmpty not have something before it? Because it is a function written within, well, it's not written yet, but isEmpty, this is a function that we're about to write. Remember, we're going to write this function. So we can call the function, this is like kind of like the idea of expand capacity. We can call a function written within the same class without having to put something in front of it. If we want to get fancy, we could do this, and this is, like we could write this, which is fine. It'll say like, okay, from this object, call this method. But we don't need the this really in this case. But I guess let's put it back in to make it more obvious. Because if, and remember too, like if I'm in my, let me go to like where my main is. See, like, this is the instance, and I'm calling isEmpty on the instance of something. But from within the instance, from within the code that defines what the object is, we don't, like, we can just write, like, isEmpty. Just like with the array stack. Where's the array stack? Do I not have an array stack here? Int array, I guess I don't. Well, whatever. Just like in the array stack, we called expand capacity. We didn't need to put anything in front of expand capacity. We just called the function, the method expand capacity. Linked stack, okay, whatever. Does that answer your question? Cool. All right, so there's our Enqueue. Now we have our Dequeue. All right, well, let's, every year we always joke. Is it just me, or do I really want to go to Dairy Queen now? Oof. So we've got our Dequeue. Well, like the stack, if it's empty, what are we gonna do? Well, we'll throw the exception. Because I don't know what you want to do as the person using the stack that I'm writing, or using the queue that I'm writing. I don't know what you want to do if you try to pop from an empty stack. Do you want the program to crash? Do you want it to ignore the problem? Do you want it to prompt the user for an additional input? I don't know. But by throwing an exception, that makes it someone else's responsibility to deal with this exceptional situation. All I'm doing is noting that this is the exceptional situation here. Okay, I create a pointer to delete that points to front. I get the data from front. I set front to point to its next, decrease count. I have to do this funny check here though, because if it's now empty by updating count, we're going to want to update rear to null pointer. And I'll show you what happens here. And this right here is so common of a mistake that I'm going to take the time to really emphasize it. But then after that, we're going to delete to delete and then return result. Okay, so once again, let's draw this out. Let's do the general case first, and then we'll do the edge case of, well, what happens if we remove something and now it's empty? So we have front points to this, which points to this, which points to this, which points to nothing, and this is rear. So this is a general case. So what are we going to do? Well, we make a new pointer called to delete and have it point to front. We get the result out of it is now equal to whatever was in here. I'll just put the E. Okay, great. So this is the thing I'm going to return eventually. Front, you're now equal to get your next. So front, be whatever comes after what you were just pointing to. Perfect. It's not empty, so we skip that. Now delete to delete. So we delete this. Good stuff. And return result. So we return whatever E was. Fantastic. We dequeued. It's beautifully clean. Now, let's see what happens though if we have front, and pay attention because this will bite you if you're not paying attention. This is the scenario. I create to delete, and remember this points to null, points to this. I get result, and I set it equal to whatever the data was. I now say front, point to your next. Good. So front will now point to null, which is what we want when the queue is empty. Now, let's see what would happen if we don't do this check. I delete this thing, and I return result. Great. But front is pointing to null, and rear is not pointing to null. Rear is pointing to somewhere in RAM that it thinks is a node, but we just deleted it. So rear is pointing to something that doesn't exist. But when the queue is empty, we want both front and rear to be pointing to null. That's an indication that it is in fact empty. In fact, we can write our isEmpty function to say, does front equal rear equal null pointer? Then we know it's good. We can also just check the count because we're keeping track of the count, but that would work. So we've got a funny situation where we're like, well, okay, hold on. This is pointing to somewhere else in RAM, not null pointer, but to some arbitrary location in RAM. So that's why this check is so important. If it's empty, rear, don't point to that random place in RAM to a node we just deleted. Point to null as well. So now we're safe. This is a very important step. Okie dokie. Oh, let's get first. This is an easier version of the Dequeue. Just if it's empty, return or throw the exception. Otherwise, return the data. But leave the node at the front of the queue that contains the data. We leave it there. It doesn't get removed. All right, here's our size, and here's our isEmpty. Okay, size, return count. IsEmpty is count 0. Okay, perfect. We're good to go. Now I think the only thing we're missing is our deconstructor and our copy constructor. So I'm just going to copy this in and then we'll talk about it. Okay. So the copy constructor. All right. How deep does this copy go? Well, I'm probably going to want to make a copy of like the containers, but I can't go all the way down because like what is T? Is it an integer or a pointer to an integer? I don't know. So I'm going to make copies of whatever the data is, whatever value is stored in data, whether it's a pointer or a value like an integer. But I'm going to absolutely have to make a complete new node for every node that I want in my queue. Because otherwise, I will have this situation. If I have front, rear, I want to make sure I'm not just creating a new queue over here and going, oh, front, you point to the same thing, because suddenly we've got an issue. It's pointing to the exact same node. If I dequeue from this queue, suddenly it affects this queue, which is problematic. So we're definitely going to make a copy of whatever's in here. So we're going to make a copy of these nodes, but I don't know what the data is. Is the data a pointer to something? Or is the data just some value like the number 1? I don't know. So I'm just going to make a copy of whatever the data is inside of here. So 1. In this case, if it's just integers, I'm happy. But if it's pointers, I could run into trouble. Let's say I'll draw it as a box, because now we've got a queue pointing to the same object, but this is kind of outside of the realm of what I'm worried about as the queue implementation. The user of the queue is going to have to be the one aware of this problem, of how deep is this copy. Have I been recording this lecture? I hope to God I have. Okay, thank goodness. Ooh. Okay, so there's our, oh, okay, so what are we doing now? Well, create a new pointer that points to the thing we're copying's front. If cur is not null, we're going to, and this is actually brilliant here. Brilliant isn't the right word. This is a good use of not making redundant code and just making use of code that already does what we need it to do. What we're doing, we have, here's our old queue. Front, rear. And then I'll pick a new color. Here's our new one. So I make a pointer C point to this thing. If C is not null, I'm going to Enqueue cur get data. Well, this is fantastic, because I could say, okay, C, get the data from here, whatever this is. And then what does Enqueue do? Well, let's have a look. Well, Enqueue, what does it do? Well, it takes some data, creates a new node. If it's empty, it just adds something to the queue itself. So by calling Enqueue, I will automatically create the new node, put the thing in it, and do everything I need it to do. This is glorious. So what I do is I say, okay, well now front points to this, rear points to this. because we enqueued this. This is fantastic. And now cur equals cur get next. Okay, cool. Is it null? No. All right, enqueue it. Perfect. Okay, so now this goes here. This gets updated to this. Cur next. Okay, you go there. Enqueue it. Okay, go to next. Well, now it's pointing to null, so it's done. Oh my goodness, I forgot to update this rear. I know it's getting kind of jumbled, but that's what's happening. So by doing enqueue, remember we could do this, right? We're saying, okay, enqueue, like, hey, you're like enqueue to yourself, which is awesome. I love this. This is perfect. If you're wondering, wait, how does it know which enqueue to call? How come it's not calling calling the original queues enqueue and not my enqueue? Well, that's because that's what the this is. If I wanted to call the original queues enqueue, I would say obj enqueue. Where's my enqueue option here? Is it because can I only access the attributes and not the? Why can I not call the object? Well, now I've lost my place. No. I would have to call the linked queues. I would have to call this specific instance's enqueue, but now I'm calling my instance, the thing that is creating itself, the thing that's copying from the other one. I get away with the this, or not even the this, because I'm just immediately doing the enqueue on me. If you're the queue I'm making a copy of, I look at your data and then I tell myself to enqueue that data into myself, which is awesome. I know it can seem weird, but it checks out, trust me. And now the deconstructor. Well, all we gotta go is just call dequeue. If you're not empty, keep dequeuing. And you might be saying, but hold on, where's all the deletes? Well, let's go have a look at dequeue. It deletes, it just removes everything for me and deletes it. Sure, it returns a result, but I don't give a crap about what's being returned. I don't care, I'm deleting it. Whatever the data is, whatever the element that we are enqueuing that had been enqueued into the queue, it might be a pointer that needs to be deleted, but I don't care about that. I, as the queue, am only responsible for the nodes that I created, because someone else somewhere created the things that are the data. So I only need to delete these things. This is fantastic. I just do all this, I go through, I dequeue until there's nothing left to dequeue, and then I know I've deleted everything. So this just automatically empties out the queue. This is magical, I love this. So what does the CPP file look like? Well, we should all know the answer to this. It looks like this. Just include the linked queue. That's it. Because these templates here will generate the code for us. Isn't that neat? I think it's pretty neat. This lecture gave us an opportunity to, not only did we learn about building a linked queue, not only did we learn about a queue, but it also gave us an example to like, look, we already wrote the code to do this. We already wrote the code to dequeue, which is effectively what I want to do to delete. We already wrote the code in queue, which I can use to make a copy. It's fantastic. I love it. It's glorious. Anyways, we'll end here. Everyone have a good weekend. Try to relax as best you can. Remember the assignment deadline has been pushed back a week. And what else did I want to say? And I guess for those of you that have lab today, well, I'll see you later today. Anyways, see you all later and try to enjoy your weekend.